हेलो डियर फ्रेंड्स। तो आज का जो हमारा टॉपिक है दैट इज अबाउट लॉरेंट्ज़ गेज एंड इन आवर प्रीवियस टॉपिक वी हैव डिस्कस्ड दैट व्हाट इज कूलम गेज and how we can with the help of this Coulomb gauge, with the Coulomb condition, how we can separate that scalar and vector potentials and how to calculate from those potentials electric and magnetic field, right? जो हमने already discuss किया। तो अगर हम ये इक्वेशन जो हमारी इक्वेशन थी from our previous topic, previous lecture, our magnetic field was that it was the curl of that vector potential, A is vector potential. And similarly, electric field I can write in terms of that minus gradient of phi, that scalar potential, and change of that rate of change of that vector potential, right? And these are our two inhomogeneous differential equations. Why these are called inhomogeneous? Because there is that source term present. This is our torque density, and this is our current density. And there is one more notation that I already discussed it in previous lecture. This is our it is called a Daylight motion. So this is called this Daylight motion is again that Laplacian operator. तो अगर हम इस पे if we have a look on this term, तो यहाँ पे जो हमारा डेल्टा स्क्वायर है, दिस इज नेबुला स्क्वायर माइनस 1 बाई सी स्क्वायर पार्शियल 2 बाई पार्शियल टी 2। तो जो इसकी फर्स्ट टर्म है दैट नेबुला स्क्वायर हमें देता है सिंपली दोज स्पेस कोऑर्डिनेट्स दैट्स पार्शियल बाई पार्शियल एक्स, पार्शियल बाई पार्शियल वाई एंड पार्शियल बाई पार्शियल जेड। एंड ये हमारा टाइम कंपोनेंट है, राइट? सो दैट मीन्स जो हमारा ये ऑपरेटर है इट इज अगेन लैप्लाशियन ऑपरेटर। ये हमारा लैप्लाशियन ऑपरेटर है बट इन फोर डायमेंशनल स्पेस। सो दैट मीन्स वी हैव दैट स्पेस कंपोनेंट एंड टाइम कंपोनेंट। सो व्हाई देयर इज माइनस साइन? बिकॉज as per that sign convention, our Minkowski schematic, so there should be either time component should be negative and space component should be positive। और इसका हम रिवर्स भी ले सकते हैं। तो उस टाइम पे हमें वी कैन टेक माइनस नेबुला स्क्वायर प्लस 1 बाई सी स्क्वायर पार्शियल 2 बाई पार्शियल टी 2। सो दैट मीन्स हमें दो में से एक लेना है, एक पॉजिटिव लेना है टाइम कंपोनेंट, देन स्पेस कंपोनेंट शुड बी नेगेटिव। तो इसका एक मेन रीजन है बिकॉज व्हेन वी मेक ट्रांसफॉर्मेशन फ्रॉम वन फ्रेम टू अनदर फ्रेम, so the length element should remain invariant। तो ये तभी invariant रहता है when we take that one negative in comparison with the rest one, right? Time is negative, space components are positive। Okay, come back to our main topic। तो ये जो हमारी these are called second order inhomogeneous differential equations and these are very difficult to calculate। तो मैंने आपको ऑलरेडी बताया कि कॉलम गेज में हम क्या करते हैं, we are simplifying or we decouple that our those second order inhomogeneous differential equations into that scalar and vector potential separately, right? So from when we calculate that scalar and vector potential phi and a, we substitute that phi and a in these equations and it gives us that electric and magnetic fields, right? Now, our next topic, today's topic is that is about Lorentz gauge. So we have one more gauge condition. So that is called a Lorentz gauge. So in Lorentz gauge condition, what we do, we assume that we put that nebula dot. So this is our Lorentz condition. Okay. So this is our Lorentz condition. तो हमें क्या करना है, दिस टर्म इसको हमें जीरो लेना है। तो अगर सपोज दिस इक्वेशन ए एंड दिस इक्वेशन बी, तो अगर हम पहले फर्स्ट इक्वेशन को सॉल्व करेंगे, क्योंकि हमें क्या देखना है कि हमें सेपरेट करना है स्केलर एंड वेक्टर पोटेंशियल from each other so that it is easy to calculate it a solution, so it is easy to calculate that scalar or vector potential now। So if we substitute it in equation first, तो first equation में हमें क्या करना है, तो if we choose this Lorentz gauge, so that means our nebula dot A should be equal to, so we will substitute now nebula dot A in this equation, in equation A। So when I use this in equation A, so we'll get that nebula square phi Now, okay, so let us use it in this equation. So that means this equation becomes, okay. Now इसकी तरफ अगर हम देखेंगे तो ये जो ब्रैकेट वाली टर्म हमारी है तो ये हमारा डेलम्बर्शन ऑपरेटर बिकॉज और दैट डेल्टा स्क्वायर इज दैट इज डेल्टा स्क्वायर. Okay, so that means this equation becomes, okay, so this is our first equation. Okay, so let us write now. Okay, so let us write now second equation. Second equation is our, so second inhomogeneous differential equation is, that is, G. Okay, so this is our second inhomogeneous differential equation. Just check your note. So ये हमारी second inhomogeneous differential equation with Soros term as our G, right? Current density. Now, if I impose this condition, तो हमारा जो Lorentz gauge है, if you remember that, our Lorentz condition is that's lambda dot A plus 1 by C square. So this is our Lorentz gauge. So ये हमारा Lorentz gauge है. Let us use this gauge in this equation, in second equation. So this becomes equal to, so this equation is another this, it's again in homogeneous differential equation, but it is very easy to calculate क्योंकि अगर हम इक्वेशन सी और इक्वेशन डी में अब हम देखेंगे क्योंकि हमने इन पे इम्पोज किया है, we use this Lorentz condition. So with the help of this Lorentz gauge, we separate that scalar and vector potential from each other, right? So this is now our decoupled equation. So phi separate है, phi is separate here, so phi is in terms of rho and A is in terms of J. तो यहाँ पे अगर हमें charge density पता होगी, so if you know the charge density of a given system, we can calculate that scalar potential, right, by this equation. So it's very easy to calculate. And similarly, if we know the current density, so you can calculate this vector potential. So that means if you calculate A from here, phi from here, so then we can write that because our B equal to, that is lambda cross A, and E equal to, ओके, तो ए हमें यहां से मिलेगा, how you can calculate from equation C. So use this in this equation, we can calculate electric and magnetic field. So what we have concluded from this topic, from this lecture. So we conclude one thing, that with the help of these gauge conditions, we are able to solve these second order differential inhomogeneous equations by decoupling, by separating that scalar and vector potential from each other. Now there is one more interesting fact about these gauges. So we have now two gauges. So one is called that Lorentz gauge. So what we have discussed it today, and another gauge that we discussed it in previous topic, that is called Coulomb gauge. So this is our Lorentz gauge, and similarly we have one more gauge, that is Nebula dot A. That's equal to 0. So this gauge is our. Now there's a difference between these. Because if you have a look on these two gauges, so first is our Lorentz gauge and second is Coulomb gauge. So this Coulomb gauge, it is in the 3 dimension, because when you calculate, when you write this nebula, you can write this in terms of that. If you calculate this value, so this will be that partial A x by partial x. Right? So this is our Coulomb gauge. So that means जो हमारा Coulomb gauge है, so it is not invariant. It doesn't remain invariant if you move from one frame to another frame. It only includes the 3 dimensions. Now, if we have a look on the another gauge condition, that's called Lorentz gauge. So Lorentz gauge में हमारा vector potential है, space components and one time component. So that means it includes that scalar as well as vector potential. But this Coulomb gauge only includes the vector potential. So that means this Lorentz gauge is Lorentz invariant. So ये Lorentz invariant है. It remains invariant when you move from one frame to another frame, because we are working in that 4 dimensional Minkowski space. So that means we should have 4 dimensions of potential. So that is only present in the Lorentz gauge A and phi. This is that scalar potential, but we don't have scalar potential in this Coulomb gauge. So this was the main difference between Coulomb and Lorentz gauge. And I repeat once again, that they help us to solve these inhomogeneous second order differential equations and how to calculate this electric and magnetic field. Right? So there are so many problems. Now there's a problem on this Coulomb and Lorentz gauge. Suppose if an electric field is given. Suppose I will take an example. If तो अगर हमें अब this is one problem on this Lorentz gauge. So if our electric and magnetic fields are unchanged, so that means हम gauge condition क्यों use करते हैं? So if we add some parameter to that our vector or scalar potential, the total electric field and magnetic field remains unchanged. So this is very important. So what I am saying now, if electric and magnetic field is unchanged, if we transform this A vector to A plus r cap, and this r cap is that's unit vector, it's r vector divided by mod of r. So we need to calculate what will be then phi at that point. Right? So this is very simple, because if you calculate here that our r vector is, that is here, r vector is r cap equal to r cap divided by mod of r, right? And what is this vector potential? So this vector potential goes from A to A plus nebula of Z. So that means अगर आपको पता होगा कि जब हम वेक्टर पोटेंशियल चेंज करें, we are going from A to A plus gradient of some scalar quantity, right? So that is if you make this change in vector potential, the total electric and magnetic field, those maximum equations remains invariant, those remain the same, तो उन पे कोई इफेक्ट नहीं पड़ेगा if we change A to A plus nebula of. Now if we have a look on this, so if we compare this with this, so that means if you compare this with this equation, so you can write that that delta lambda will be equal to R, right? So, but what is lambda here? So lambda equal to, so you can write this as, what will be delta lambda then? So that will be equal to partial lambda by partial R into R. So that will be equal to, because partial lambda by partial, if we compare this equation, so partial lambda by partial R will be equal to 1. So which implies that partial lambda by partial R will be equal to, right? So we need to add the scalar potential. So if we integrate this equation, when you integrate this equation, partial lambda by partial R, so that's equal to 1, or you can write that our lambda will be equal to R plus. Okay. So what will be the scalar potential then? So they हमने क्या किया? Because अगर हम compare करेंगे ये वाली equation with this, because we are writing the vector potential as A plus some gradient of some scalar quantity. So that means if you compare this equation with this equation, so that means delta lambda will be equal to r cap, right? तो वहां से मिलेगा मुझे lambda partial lambda by partial r, that should be equal to 1. Or if you integrate this equation, you can get lambda equal to r plus c. So that अब हमें देखना है कि scalar potential हमें कितना change करना है. So if we check now, what will be our that lambda, or you can check now, if you write now what's our phi dash, so phi dash will be equal to phi minus partial lambda by partial of t, right? So that means this will be equal to phi minus partial by partial t of r plus. Okay, so that means अगर हम वेक्टर पोटेंशियल इतना चेंज करेंगे, that a to a plus r क्या, तो उस टाइम पे हमें स्केलर पोटेंशियल इतना चेंज करना है, और you can write phi dash here. Okay. So इतना हमें स्केलर पोटेंशियल चेंज करना है, so that our this electric and magnetic field remain invariant. So this is so there are so many problems. Hopefully in coming lectures we will discuss about some more problems on these gauge transformations, as well as some new topics that will help you in your future. Thank you.